Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. Why nothing can go faster than light. Light moves at exactly 300,000 kilometers per second in a vacuum, fast enough to circle Earth more than 7 times in a single second. This speed seems arbitrary at first, just another number to memorize. But the speed of light represents something far more profound than a mere velocity. It's a fundamental limit built into the structure of the universe itself, a cosmic speed limit that nothing with mass can reach, let alone exceed. Understanding why nothing can go faster than light means understanding one of the most revolutionary insights in physics, that space and time are not separate, unchanging backdrops to events, but are woven together into a unified fabric that behaves in deeply counterintuitive ways. Before Albert Einstein published his special theory of relativity in 1905, most physicists assumed that velocities simply added together in straightforward ways. If you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, then someone standing beside the tracks would see the ball moving at 70 kilometers per hour. This common sense addition of velocities works perfectly well at everyday speeds. But Einstein realized that this intuitive picture breaks down at velocities approaching the speed of light, and the breakdown reveals something fundamental about the nature of space and time. Einstein started with 2 basic principles. First, the laws of physics should be the same for everyone moving at constant velocity, regardless of how fast they're going. This principle of relativity had been around since Galileo, and it accords with common experience. You can't tell from experiments done inside a smoothly moving train whether the train is moving or the station is moving past you. Second, and more radically, Einstein proposed that the speed of light is the same for everyone, regardless of how fast they're moving or how fast the light source is moving. This second principle contradicts our everyday intuition about velocity addition. If you're on a train moving forward and you shine a flashlight forward, you might expect someone on the platform to measure the light going faster than someone on the train would measure it, by an amount equal to the train's speed. But experiments repeatedly showed that this doesn't happen. The person on the platform and the person on the train both measure exactly the same speed for the light. This bizarre result seems impossible if we assume that space and time are absolute and unchanging. Einstein's breakthrough was realizing that space and time must not be absolute. Instead, they must adjust themselves to keep the speed of light constant for all observers. When you move faster, time actually slows down for you relative to someone standing still, and distances contract in your direction of motion. These effects, called time dilation and length contraction, are not optical illusions or measurement errors. They're real physical changes in how time flows and how space extends. At everyday speeds, these relativistic effects are incredibly tiny, too small to notice. A person traveling in a car at highway speed experiences time flowing more slowly than someone standing still, but the difference amounts to only billionths of a second over a lifetime. But as speeds approach the speed of light, these effects become dramatic. At 90% of light speed, time runs at only about 44% of the normal rate. At 99% of light speed, time runs at about 14% of normal. As you get closer and closer to light speed, time slows down more and more dramatically, approaching a complete stop as velocity approaches the speed of light. This time, dilation has been confirmed through countless experiments. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground, by exactly the amount Einstein's equations predict. Particles called muons created when cosmic rays strike the upper atmosphere, live for only about 2 microseconds before decaying. At the speeds they travel, close to the speed of light, time dilation extends their lifetimes enough that they reach the ground before decaying, something that would be impossible if time flowed normally for them. GPS satellites must account for relativistic time dilation, both from their speed and from Earth's gravity, or they would accumulate errors of several kilometers per day. Length contraction is equally real. A spaceship traveling at 99% of light speed would be compressed to about 14% of its rest length in the direction of motion from the perspective of someone watching it pass by. From the crew's perspective, inside the ship, they wouldn't feel compressed. They would measure their ship as having its normal length, but they would measure the distance to their destination as being contracted, appearing much shorter than it does to someone at rest relative to the destination. These strange effects arise from the fact that the speed of light must be the same for everyone. If you're chasing a beam of light at 99% of light speed, you still measure that light beam as moving away from you at full light speed, not at 1% of light speed, as you might expect. This only makes sense if time is flowing more slowly for you, and distances are contracted in your reference frame. The adjustments exactly compensate to keep the speed of light constant. But what happens if you try to accelerate something to light speed? Here's where the cosmic speed limit becomes absolute. As an object with mass accelerates, it gains kinetic energy. In classical physics, kinetic energy depends on velocity in a simple way. Double the velocity, and kinetic energy increases by a factor of 4. But Einstein showed that the relationship changes as you approach light speed. The energy required to accelerate an object increases more and more dramatically as velocity increases, and as you approach light speed, the energy required approaches infinity. This happens because of something called relativistic mass increase. As an object moves faster, it becomes harder to accelerate. It behaves as if it's getting more massive. At 90% of light speed, an object has about twice its rest mass. At 99%, it has about 7 times its rest mass. As velocity approaches light speed, the relativistic mass approaches infinity. To actually reach light speed would require infinite energy to accelerate infinite mass, a physical impossibility. Light itself travels at light speed because photons, the particles of light, have no mass. Maxwell's equations, which describe how electromagnetic fields behave, predict that electromagnetic waves travel at a specific speed determined by properties of space itself. Einstein realized that this speed is the cosmic speed limit, and that massless particles must travel at exactly this speed. Photons don't have to accelerate to light speed. They're created already moving at light speed, and they can never slow down or stop as long as they exist. Other massless particles like gluons, which carry the strong nuclear force, also travel at light speed. Gravitational waves, ripples in space-time itself, travel at light speed as well. Mass is what prevents particles from reaching this ultimate speed. Any particle with mass can approach light speed arbitrarily closely if given enough energy, but can never quite reach it. The relationship between energy, mass, and velocity is captured in Einstein's famous equation, E equals mc squared, though this is actually a special case of a more general equation. The full equation shows that total energy equals the rest mass energy plus kinetic energy, and as velocity increases, more and more of the total energy goes into the kinetic energy component. At very high velocities, most of the energy is kinetic rather than rest mass. Particle accelerators demonstrate these principles directly. The Large Hadron Collider accelerates protons to more than 99.99% of light speed. At these velocities, the protons have about 7,000 times more energy than their rest mass energy. Accelerating them to even higher velocities, getting closer to light speed, requires exponentially more energy for each incremental increase in velocity. No matter how much energy you put in, the protons never quite reach light speed, and the energy required to actually reach it would be infinite. Some people wonder whether traveling faster than light might be possible by warping space rather than moving through it. General relativity does allow for exotic spacetime geometries, like wormholes or warp drives, that could theoretically allow effective faster-than-light travel without actually moving through space faster than light. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a theoretical way to contract space in front of a spacecraft and expand it behind, allowing the spacecraft to effectively travel faster than light while locally moving slower than light relative to the space immediately around it. However, these solutions require exotic matter with negative mass or negative energy density, properties never observed and possibly forbidden by quantum mechanics. Even if such matter could exist, the energy requirements would be astronomical, potentially requiring more energy than exists in the entire observable universe. These remain purely theoretical concepts, with no practical pathway to implementation, and they don't violate the fundamental principle that nothing can move through space faster than light. The cosmic speed limit has profound implications for space travel. Even at light speed, it would take over 4 years to reach the nearest star beyond our Sun, Proxima Centauri. Travelling to the centre of our galaxy would take over 25,000 years at light speed. Reaching nearby galaxies would take millions of years. The vast distances between stars and galaxies, combined with the absolute speed limit, mean that interstellar travel remains extraordinarily challenging even in principle. For travellers moving at near light speeds, time dilation provides a partial solution. From the crew's perspective, a journey might take only months or years, while decades or centuries pass on Earth. This time dilation allows relativistic travellers to cross vast distances within their own lifetimes, though everyone they knew would age far more or be long dead by the time they returned. This creates a fundamental asymmetry. The traveller's time and the stay-at-home's time flow at different rates, and there's no way to make them match up again. The speed of light also limits how quickly information can travel. When you see a star in the night sky, you're seeing it as it was years or centuries ago. That's how long the light took to reach you. The sun you see is 8 minutes in the past. If the sun suddenly vanished, we wouldn't know for 8 minutes. This light travel time creates what physicists call a light cone, the boundary between events that can influence you and events that cannot because they're too far away in space and too close in time for light to have travelled from there to here. Causality itself depends on the cosmic speed limit. If information could travel faster than light, it would be possible to send messages backward in time, to communicate with your own past. This creates logical paradoxes, like sending a message to your past self, telling yourself not to send the message. The speed of light limit prevents these paradoxes by ensuring that cause always precedes effect for all observers, regardless of their motion. The universe seems designed in a sense with this speed limit built in. Light speed isn't just the speed at which light happens to travel, it's a fundamental property of space-time itself, woven into the structure of reality. Mass is what prevents particles from reaching this ultimate speed, and the closer you get to it, the more energy is required to go faster, asymptotically approaching infinite energy at the limit. This speed limit connects space and time in an intimate way. Space and time aren't separate entities but are aspects of a unified, four-dimensional space-time. Events that appear simultaneous to one observer might not be simultaneous to another observer moving differently. The cosmic speed limit defines the structure of this space-time, determining how space and time mix together as observers change velocity. Why nothing can go faster than light ultimately comes down to the structure of space-time itself. The speed of light isn't a speed limit in the sense of a rule imposed from outside, it's a fundamental property of how the universe is built. how space and time relate to each other, and how energy and mass behave. Reaching light speed would require infinite energy. The only things that can travel at light speed are things with no mass, like photons, which must always travel at this speed. Everything else, everything with mass, can only approach this ultimate velocity, forever accelerating, but never quite reaching the cosmic speed limit that defines the maximum rate at which anything can travel through the fabric of space-time. Why some objects in space are heavier than others. When you hold a rock in one hand and a piece of styrofoam the same size in the other, the difference is immediately obvious. The rock is heavier. This difference comes from density, the amount of mass packed into a given volume. The same principle operates throughout the universe, but on cosmic scales, the variations in density become far more extreme than anything we encounter in daily life. Understanding why some objects in space are heavier than others means understanding how matter behaves under different conditions of temperature, pressure, and gravity, and how the history of an object determines what it's made of, and how tightly that material is packed together. Start with the simplest objects in space, clouds of gas in the interstellar medium. These clouds are extraordinarily diffuse, containing perhaps only a few atoms per cubic centimetre. In comparison, the air you breathe contains about 25 billion molecules per cubic centimetre. The density of interstellar gas is so low that the best vacuum we can create on Earth is still millions of times denser. These gas clouds have mass, sometimes thousands or even millions of times the mass of the Sun, but it's spread across such enormous volumes that the density is essentially zero by any terrestrial standard. Planets show a wide range of densities depending on their composition and formation history. The gas giants Jupiter and Saturn are primarily hydrogen and helium, the lightest elements. Jupiter's average density is about 1.3 grams per cubic centimetre, only slightly denser than water. Saturn is even less dense at 0.7 grams per cubic centimetre. It would float in a bathtub if you could find one large enough. This low density reflects their composition, dominated by the lightest elements in the universe, compressed by their own gravity, but not enough to create extremely high densities. The rocky planets of the inner solar system are much denser. Earth has an average density of 5.5 grams per cubic centimetre, about 4 times denser than Jupiter, despite being much smaller. This difference comes from composition. Earth is made primarily of rock and metal, silicates in the mantle and crust, iron and nickel in the core. These materials are intrinsically denser than hydrogen and helium. Silicon, oxygen, magnesium, and iron atoms are much more massive than hydrogen atoms, and when they bond together into minerals and metals, they pack together more tightly than gases can. Mercury, the innermost planet, is even denser than Earth at 5.4 grams per cubic centimetre, despite being much smaller. For a small planet, this density is surprisingly high, and it tells us that Mercury must have an unusually large iron core relative to its size. The leading theory, developed by planetary scientists studying how planets form, suggests that a massive impact early in Mercury's history stripped away much of its rocky mantle, leaving behind a planet that's mostly iron core, with only a thin shell of rock surrounding it. The iron, being much denser than rock, gives Mercury its high density. White dwarfs represent a dramatic jump in density. These are the remnants of stars like the Sun after they have exhausted their nuclear fuel and shed their outer layers. What remains is the core, compressed by gravity but supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. A white dwarf packs roughly the mass of the Sun into a sphere about the size of Earth, creating densities around 1 million grams per cubic centimetre, or 1 metric ton per cubic centimetre. A teaspoon of white dwarf material would weigh about 5 tons on Earth. This represents matter compressed to the point where atomic nuclei are essentially touching, with electrons flowing between them in a degenerate electron gas. Subramanian Chandrasekhar calculated in the 1930s that there's a maximum mass for white dwarfs, about 1.4 times the Sun's mass, now called the Chandrasekhar limit. Above this mass, electron degeneracy pressure cannot support the star against its own gravity, and further collapse occurs. This calculation, which earned Chandrasekhar the Nobel Prize decades later, explained why some stellar remnants become something even denser than white dwarfs. Neutron stars take density to an even more extreme level. When a massive star's core collapses in a supernova, if the core's mass exceeds the Chandrasekhar limits, but is below about 3 solar masses, it compresses beyond the point where electron degeneracy can support it. The electrons are forced into the protons, combining through inverse beta decay to form neutrons. The result is a neutron star, a sphere about 12 miles across containing 1 to 2 solar masses. The density at a neutron star's center reaches about 500 million to perhaps 1 billion tons per cubic centimeter. This is comparable to the density inside an atomic nucleus, meaning a neutron star is essentially a single gigantic nucleus held together by gravity rather than the strong nuclear force. At these densities, matter behaves in ways impossible to replicate in laboratories. The neutrons exist in a superfluid state with zero viscosity. The outer crust is a crystalline lattice of neutron-rich nuclei. Deeper down, neutrons drip out of nuclei and flow freely. At the very center, densities might exceed that of atomic nuclei, and matter might transition into exotic states, quark-gluon plasma, where neutrons dissolve into their constituent quarks, or other forms of matter predicted by quantum chromodynamics, but never observed. Black holes represent the ultimate extreme of density, though their density is somewhat paradoxical. The matter that forms a black hole collapses to a singularity, a point of infinite density, where general relativity predicts that space-time curvature becomes infinite. The singularity is hidden behind the event horizon, and we can meaningfully talk about the average density within the event horizon. For stellar mass black holes formed from collapsed stars, this average density is extraordinarily high, but for supermassive black holes containing millions or billions of solar masses, the event horizon is so large that the average density within it can be quite low, sometimes less than water for the largest black holes. This doesn't mean the black hole's interior is actually that density, just that if you calculated density by dividing total mass by the volume enclosed by the event horizon, you would get that number. The density variations we observe in the universe reflect the different physical processes that create and shape cosmic objects. Gas clouds have low density because gravity hasn't compressed them significantly. Thermal pressure from their temperature balances gravity, maintaining their diffuse state. Planets have intermediate densities determined by their composition, which depends on where they formed in the protoplanetary disk and what materials were available. Rocky planets formed close to their stars where it was too hot for ices to condense, while gas giants formed farther out, where ices could exist and helped build massive cores that captured hydrogen and helium. Stellar remnants have high densities because they are supported not by thermal pressure, but by quantum mechanical degeneracy pressure. As physicist Wolfgang Pauli explained in formulating the exclusion principle in 1925, fermions, particles like electrons and neutrons, cannot occupy identical quantum states. When you try to compress them, they resist because there are no available quantum states for them to occupy. This quantum pressure can support matter to much higher densities than thermal pressure can, but only up to certain limits determined by the mass and the type of fermion providing the support. Temperature also affects density. Hot gas is less dense than cold gas at the same pressure because the particles move faster and push outward more strongly. This is why hot air rises. It's less dense than the cooler air around it. In space, hot gas in the coronas of stars, or in galaxy clusters has lower density than cooler gas in molecular clouds, even when both regions have similar pressures. The Sun's core, where temperatures reach 27 million degrees Fahrenheit, has a density of about 150 grams per cubic centimetre, dense by terrestrial standards, but far less dense than a white dwarf, even though the Sun's core is much hotter. The difference is that the Sun is supported by thermal pressure from ongoing nuclear fusion, while a white dwarf is supported by electron degeneracy pressure after fusion has ceased. Composition fundamentally determines the density any object can achieve under given conditions. Hydrogen, the lightest and most abundant element, naturally produces lower density objects than heavier elements. This is why gas giants, primarily hydrogen, are less dense than rocky planets made of silicon, oxygen, and iron. But composition interacts with pressure in complex ways. Under the extreme pressures inside Jupiter, hydrogen is compressed into a metallic state, denser than solid hydrogen would be under normal conditions, though still less dense than rock or metal. The formation history of an object determines both its composition and its density. Early in the solar system's formation, different materials condensed at different temperatures as the protoplanetary disk cooled. Close to the Sun, only metals and rocks could condense. These became the rocky planets. Farther out, where temperatures were lower, water ice could condense, providing additional solid material that helped build larger cores. These larger cores could then capture hydrogen and helium gas before the solar wind swept it away, forming gas giants. Farther still, at the coldest reaches, methane and nitrogen ices could condense, contributing to objects like Pluto and other Kuiper Belt objects. The history of compression matters too. Jupiter's core is thought to be compressed rock and ice, squeezed by the weight of the hydrogen and helium above it, to pressures millions of times Earth's atmospheric pressure. Under these conditions, materials that started as ordinary rock and ice are compressed to much higher densities, possibly exceeding even the density of iron under normal conditions. The exact state of matter under such extreme pressures remains uncertain. Laboratory experiments can replicate some of these conditions, but not the combination of extreme pressure, temperature, and scale found in giant planet interiors. Rotation affects density distributions within objects. A rapidly spinning object experiences centrifugal forces that cause it to bulge at the equator and flatten at the poles. This changes the density distribution, making the equatorial regions less dense and the polar regions denser. Saturn, spinning rapidly and composed largely of fluid, shows a noticeable oblate shape. Its equatorial diameter is about 10% larger than its polar diameter. Neutron stars spinning hundreds of times per second bulge significantly at their equators, altering their density distributions and affecting how they emit radiation. Throughout the universe, from the near vacuum of intergalactic space containing less than 1 atom per cubic meter, through the varied densities of planets, stars, and stellar remnants, to the extreme densities of neutron stars and the singularities within black holes, density varies by factors of hundreds of billions of billions. These variations reflect the different conditions under which matter exists, the temperatures, pressures, compositions, and quantum mechanical states that determine how tightly matter can be packed together, creating the extraordinary range of cosmic objects we observe, each with its own characteristic density, telling the story of how it formed and what forces shape its structure. Why stars explode when they die? For millions or billions of years, a star exists in a state of perfect balance. Gravity pulls inward, trying to compress the star, while the heat and pressure from nuclear fusion in the core push outward, resisting that compression. This equilibrium, this careful balance between opposing forces, allows stars to shine steadily for incomprehensible stretches of time. But eventually, inevitably, the fuel runs out. For some stars, death comes quietly, a gentle fading as they shed their outer layers and cool into obscurity. But for the most massive stars, death is anything but peaceful. When these giants exhaust their nuclear fuel, they don't fade. They explode with such violence that a single dying star can briefly outshine an entire galaxy of hundreds of billions of stars. The path to a supernova explosion begins with the structure of massive stars and how they generate energy. Stars like our Sun fuse hydrogen into helium in their cores, a process that releases energy and provides the outward pressure needed to support the star against its own gravity. But massive stars, those with at least 8 times the Sun's mass, don't stop at hydrogen fusion. When the hydrogen in the core is exhausted, the core contracts and heats up until it reaches temperatures high enough to fuse helium into carbon and oxygen. This is just the beginning. For massive stars, nuclear fusion proceeds through multiple stages, each burning a different fuel. After helium burning comes carbon burning, then neon burning, then oxygen burning, and finally silicon burning. Each stage produces heavier elements as its ash, and those ashes become the fuel for the next stage. Each stage also burns faster than the previous one because it occurs at higher temperatures and releases less energy per fusion reaction. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, but only days fusing silicon. The star develops a layered structure, like an onion, with each shell fusing a different element. The outermost layers still contain mostly hydrogen. Deeper in, a shell fuses helium. Deeper still, shells fuse carbon, neon, oxygen, and silicon in succession. At the very center lies an iron core, about 1.5 times the mass of the Sun, but compressed into a sphere roughly the size of Earth. This iron core is the end of the line. Iron occupies a special place in nuclear physics. Elements lighter than iron release energy when fused together. This is what powers stars. Elements heavier than iron release energy when split apart through fission, but iron sits at the peak of the binding energy curve. Fusing iron nuclei together doesn't release energy, it requires energy. The iron core cannot generate heat through fusion. It's an inert ball of matter, supported only by electron degeneracy pressure, the quantum mechanical resistance of electrons being compressed too closely together. The iron core grows as the silicon-burning shell above it continues converting silicon into iron. Each second, tons of iron are added to the core. The core is already incredibly dense, about 10 billion kilograms per cubic meter, and as it grows more massive, it also grows hotter and denser. The electrons supporting the core are squeezed into higher and higher energy states, reaching energies where they can do something remarkable. They can merge with protons. This process, called electron capture or inverse beta decay, occurs when an electron is forced into a proton, creating a neutron and releasing a neutrino. The neutrino immediately escapes from the star at the speed of light, carrying energy away. This removes electrons from the core, reducing the electron degeneracy pressure that's supporting it. The core contracts further, squeezing more electrons into protons, creating more neutrons, removing more pressure support, causing further contraction. This runaway process accelerates catastrophically. Subramanian Chandrasekhar calculated in the 1930s that electron degeneracy pressure can support a maximum mass of about 1.4 solar masses, now called the Chandrasekhar limit. When the iron core exceeds this limit, electron degeneracy pressure can no longer hold it up. The core collapses. What happens next occurs in less than a second, but releases more energy than the star produced during its entire multi-million-year lifetime. The core implodes at velocities reaching 70,000 kilometers per second, nearly 1/4 the speed of light. The outer part of the core falls onto the inner part, compressing it to densities exceeding that of atomic nuclei. At these densities, around 400 trillion grams per cubic centimeter, nuclear forces become repulsive rather than attractive. The collapse halts suddenly, like a ball hitting a concrete floor. The abrupt halt of the inner core creates a shock wave that propagates outward through the infalling material. This bounce shock wave contains enough energy to blow apart the entire star, but calculations show that it stalls within milliseconds, unable to push through the still infalling outer layers. For decades, this posed a major theoretical problem. How do stars actually explode if the bounce shock stalls? The answer lies in neutrinos. During the collapse, protons and electrons combine to form neutrons, releasing vast numbers of neutrinos. The newborn neutron star at the core, incredibly hot, temperatures exceeding 100 billion degrees, produces additional neutrinos through various processes. In normal circumstances, neutrinos barely interact with matter. Trillions pass through your body every second from the sun without causing any effect. But the matter in a collapsing stellar core is so dense that even neutrinos can't escape immediately. They diffuse outward over several seconds, and during this time, a tiny fraction, less than 1% of them, interact with the infalling material. This sounds negligible, but the total neutrino energy is staggering, about 10 to the 53 ergs, roughly 100 times the energy the sun will radiate during its entire 10 billion year lifetime, released in just 10 seconds. Even if only 1% of this energy couples to the stellar material, it's more than enough to revive the stalled shockwave and drive the explosion. The outer layers of the star are blasted into space at speeds of 30,000 kilometers per second or more. This core collapse supernova, designated Type 2 if hydrogen is present in the spectrum, or Type 1b or IC if the star lost its hydrogen envelope before exploding, is the fate of all massive stars. The explosion is so energetic that it creates elements heavier than iron through rapid neutron capture. During the few seconds of the explosion, neutrons are so abundant that nuclei can capture many neutrons in quick succession, building up elements like gold, platinum, and uranium that cannot be created through normal stellar fusion. Every atom of gold in existence was created in supernova explosions or in the mergers of neutron stars. The only direct detection of supernova neutrinos occurred on February 23, 1987, when neutrino detectors on Earth registered a burst of neutrinos from supernova 1987A in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The neutrinos arrived about 3 hours before the light became visible, exactly as predicted. The neutrinos escaped during the core collapse, while the light had to wait for the shockwave to reach the star's surface. This detection confirmed the core collapse mechanism and marked the beginning of neutrino astronomy. There's another type of supernova with a completely different mechanism, the Type 1a supernova. These occur in binary star systems, where a white dwarf, the dense remnant of a sun-like star, accretes matter from a companion star. As the white dwarf gains mass, it approaches the Chandrasekhar limit. When it crosses this threshold, carbon fusion ignites throughout the entire white dwarf, almost simultaneously, not gradually, from the center outward. The fusion releases so much energy that the white dwarf is completely disrupted. There's no neutron star remnants left behind. The entire star is blown apart. Type Ia supernovae are remarkably uniform in their energy output because they always occur at approximately the same mass, the Chandrasekhar limit. This uniformity makes them valuable as standard candles for measuring cosmic distances. Observations of distant Type Ia supernova by Saul Perlmutter, Brian Schmidt, Adam Ress, and their teams in the 1990s revealed that the universe's expansion is accelerating, leading to the discovery of dark energy and earning the observers the 2011 Nobel Prize in Physics. The energy released in a supernova is distributed across different forms. About 99% goes into neutrinos, which escape into space carrying information about the core collapse. About 1% goes into kinetic energy of the ejected material. the blast wave that expands into space. Only about 0.01% goes into light, but this is still enough to make the supernova visible across billions of light years. For a few weeks, a single supernova can outshine its entire host galaxy. The remnant left behind after a core collapse supernova depends on the core's final mass. If the core is between about 1.4 and 3 solar masses, electron degeneracy pressure fails, but neutron degeneracy pressure succeeds in halting the collapse, creating a neutron star. If the core exceeds roughly 3 solar masses, even neutron degeneracy pressure cannot stop the collapse, and the core continues collapsing into a black hole. The exact threshold remains uncertain because it depends on the equation of state of nuclear matter at extreme densities, which is not precisely known. Supernova explosions enrich the interstellar medium with heavy elements. The carbon, oxygen, silicon, and iron in the ejected material mix into interstellar gas clouds, raising their metallicity, the abundance of elements heavier than hydrogen and helium. These enriched clouds eventually collapse to form new generations of stars and planets. The Sun and Earth formed from material enriched by previous supernova. Every element heavier than lithium in your body was created in a star and dispersed by a supernova or stellar wind. The shock wave from a supernova can trigger new star formation by compressing nearby molecular clouds. The expanding remnant, a shell of hot gas and energetic particles, can remain visible for thousands of years. The Crab Nebula, visible in the constellation Taurus, is the remnant of a supernova that occurred in 1054 AD and was recorded by Chinese astronomers. At its center sits a rapidly spinning neutron star, a pulsar rotating 30 times per second, powered by the rotational energy it inherited from the collapsed core. Supernova rates in galaxies depend on the star formation rate and the mass distribution of stars being formed. The Milky Way experiences roughly 2 to 3 supernovae per century on average, though we haven't witnessed a nearby visible supernova since Kepler's supernova in 1604. Most occur hidden behind dust in the galactic plane, their light obscured but their effects, shock waves, cosmic rays, heavy element enrichment, rippling through the galaxy. The most massive stars can experience even more exotic deaths. Stars exceeding roughly 130 solar masses might become pair instability supernovae, where gamma rays in the core become so energetic that they spontaneously convert into electron-positron pairs. This removes pressure support, causing catastrophic collapse and an explosion so violent that the entire star is destroyed. No remnant of any kind survives. Stars more massive still might collapse directly into black holes without exploding at all, with all their mass disappearing behind an event horizon in silence. Understanding why stars explode when they die connects nuclear physics, quantum mechanics, general relativity, and hydrodynamics. It explains the origin of elements, the formation of neutron stars and black holes, the enrichment of galaxies with heavy elements, and the triggering of new star formation. The death of massive stars through supernova explosions is not just destruction, it's creation, recycling stellar material back into space, enriched with new elements, ready to form new stars, new planets, and perhaps new life, continuing the cosmic cycle that has built the complex, element-rich universe we inhabit today, all initiated by the catastrophic collapse that occurs when fusion finally fails and gravity wins its ultimate victory over the force that gave the star life. How asteroids can have their own moons. The first asteroid moon was discovered in 1993, when the Galileo spacecraft, on its way to Jupiter, flew past an asteroid named Ida and transmitted images showing a small companion orbiting it. The discovery surprised many scientists. Ida itself is only about 56 kilometers long, an irregular, potato-shaped chunk of rock tumbling through space. Its tiny moon later named Dactyl, measures merely 1.4 kilometers across. How could such a small object, with such weak gravity, possibly hold onto a moon? This discovery opened an entirely new chapter in our understanding of asteroids, revealing that these ancient fragments of the early solar system are far more complex and dynamic than anyone had imagined. The key to understanding asteroid moons lies in recognizing that gravity, no matter how weak, still operates according to the same laws, whether you're considering a massive planet or a tiny asteroid. Every object with mass generates a gravitational field, and that field extends infinitely into space, weakening with distance, but never disappearing entirely. An asteroid's gravity is incredibly feeble compared to a planet's. Ida's surface gravity is only about 0.3 to 1% of Earth's, depending on where you measure it, on the irregular surface. But this tiny gravitational pull is sufficient to influence nearby objects, and under the right circumstances, it can capture and hold a moon in orbit. The mechanics of orbital motion around an asteroid differ significantly from orbits around planets. Planets are generally spherical, or nearly so, which means their gravitational fields are relatively simple. They approximate the field of a point mass located at the planet's center. Asteroids, however, are often highly irregular, shaped like elongated potatoes, peanuts, or even contact binaries where two lobes are stuck together. This irregular shape creates a complex gravitational field with multiple peaks and valleys, regions where the gravitational pull is stronger or weaker than average. An object orbiting an irregular asteroid doesn't follow a simple ellipse the way a planet orbits the Sun. The orbit wobbles and shifts due to the uneven gravity field. Additionally, most asteroids rotate, and this rotation causes the gravitational field to change over time from the perspective of an orbiting object. The combination of irregular shape and rotation creates a challenging environment for stable orbits. Yet despite these complications, asteroid moons not only exist but are surprisingly common. Current estimates suggest that about 15% of near-Earth asteroids have companions, and the fraction is even higher among certain populations. Asteroid moons form through several mechanisms, each revealing something about the dynamic processes that shape these small bodies. The first mechanism is capture. Similar to how planets can capture moons, though the process works differently at asteroid scales. When two asteroids pass close to each other, they normally just fly past, perhaps exchanging some momentum through gravitational interaction, but remaining on separate trajectories. However, if a third body is nearby during the encounter, it can absorb some of the kinetic energy through a three-body gravitational interaction, allowing one asteroid to be captured into orbit around the other. This three-body capture was more common in the early solar system, when asteroids were more numerous and encounters more frequent. The asteroid belt, located between Mars and Jupiter, contains hundreds of thousands of asteroids larger than 1 kilometer and millions of smaller ones. In the denser environment of the early solar system, close encounters between 3 or more asteroids occurred regularly, providing opportunities for capture. Once captured, the orbit would gradually stabilize through tidal interactions and additional gravitational perturbations. Collisions represent another pathway to moon formation. The asteroid belt is a violent place where collisions occur regularly on geological timescales. When two asteroids collide, the impact doesn't necessarily destroy both objects. Depending on the impact velocity and angle, a collision might excavate a crater and eject material into space. Some of this ejected material falls back onto the asteroid, but some of it enters orbit around the shattered parent body. Over time, these orbiting fragments can collide with each other and coalesce into a moon. The collision scenario explains why many asteroid moons orbit very close to their parents and have compositions similar to the parent asteroid. If a moon formed from impact debris, it would naturally be made of the same material as the parent. Studies of asteroid pairs Asteroids with very similar orbits and compositions suggest that many originated as fragments from catastrophic collisions that split a parent asteroid into two or more large pieces. In some cases, these pieces remain gravitationally bound, creating a binary asteroid system. The YORP effect provides a third mechanism for creating asteroid moons, and it's one of the most fascinating processes in asteroid dynamics. YORP stands for Yarkovsky-O'Keefe-Radzievsky-Paddock, named after the scientists who contributed to understanding this phenomenon. The YORP effect occurs when sunlight reflecting off an asteroid's irregular surface creates tiny torques that gradually change the asteroid's rotation rate. The effect is incredibly small. It might change an asteroid's rotation period by only milliseconds per year, but over millions of years, these tiny changes accumulate. As the YORP effect spins an asteroid faster and faster, centrifugal forces at the equator increase. Eventually, the asteroid might be rotating so fast that material at the equator experiences outward centrifugal forces that exceed the inward gravitational forces. At this point, material begins to lift off the surface and enter orbit, forming a ring or disk around the asteroid. This orbiting material can then aggregate into one or more moonlets. Computer simulations and observations of very rapidly rotating asteroids support this mechanism. Asteroid 1999 KW4 provides a clear example of the YORP effect in action. This binary asteroid system consists of a larger primary asteroid, about 1.3 kilometers in diameter, rotating once every 2.8 hours, extremely fast for an object this size. A smaller satellite, about 360 meters across, orbits the primary at a distance of about 2.6 kilometers. The primary asteroid has a distinct equatorial ridge, exactly what would be expected if centrifugal forces had been pushing material toward the equator. The satellite likely formed from material that was flung off this equatorial region when the primary was spinning even faster in the past. The rotation rates of asteroids play a crucial role in their ability to hold moons. There's a limiting rotation rate, typically around one rotation every 2 to 3 hours for a solid asteroid, beyond which centrifugal forces would tear the asteroid apart. This limit, called the critical spin limit, depends on the asteroid's size, shape, and material strength. Asteroids can spin faster than this limit only if they're held together by internal strength, essentially solid rocks, rather than just gravity. Many asteroids appear to be rubble piles, loose aggregations of boulders and gravel, held together primarily by their own weak gravity, with little internal strength. These rubble pile asteroids cannot spin faster than the critical limit without shedding material or breaking apart. The Roche limit becomes relevant for asteroid moons, just as it does for planetary moons. The Roche limit is the distance inside which tidal forces would tear apart a satellite that's held together only by its own gravity. For solid objects held together by material strength, they can orbit inside the Roche limit without being destroyed, though they experience severe tidal stresses. Many asteroid moons orbit near or even slightly inside the classical Roche limit for a fluid body, suggesting that they're solid objects with sufficient strength to resist tidal disruption. Binary asteroids, where two similarly sized objects orbit their common center of mass, represent a special category. In these systems, neither object is clearly the moon of the other. They're more like double asteroids, co-orbiting companions. The Pluto-Charon system is arguably a binary system, though Pluto is now classified as a dwarf planet rather than an asteroid. Among smaller asteroids, binary systems are not uncommon. The asteroid Antiope consists of two objects, each about 88 kilometers in diameter, orbiting their common center of mass at a separation of about 170 kilometers. These binary systems likely form from gentle collisions or from the splitting of a rapidly rotating parent body. When an asteroid spins fast enough, it can develop a dumbbell or peanut shape, elongated along its equatorial plane. If the spin increases further, the dumbbell can split at its narrow center, creating two separate bodies. Because they formed from the same parent, they initially have very similar velocities and remain gravitationally bound, orbiting each other. Observing asteroid moons requires careful astronomical work. Most asteroids are too small and distant to be resolved as disks even through powerful telescopes. They appear as points of light. Their moons are even fainter and closer to the primary, making direct imaging challenging. However, several techniques reveal their presence. Light curve analysis measures how an asteroid's brightness changes over time as it rotates. A simple asteroid produces a regular, repeating pattern, but if a moon is present, it creates additional dips or bumps in the light curve as it passes in front of or behind the primary asteroid, or as it reflects additional light toward Earth. Radar observations provide another powerful technique. When radio waves are bounced off an asteroid, the reflected signal contains information about the asteroid's shape, rotation, and surface features. If a moon is present, it appears as a separate echo in the radar data, delayed relative to the primary's echo by the light travel time to the more distant moon. The Arecibo Observatory in Puerto Rico and the Goldstone Solar System Radar in California have discovered dozens of asteroid moons through radar observations of near-Earth asteroids as they pass relatively close to Earth. Spacecraft missions provide the most detailed views of asteroid moons. After Galileo's discovery of Dactyl orbiting Ida, subsequent missions have encountered other asteroid systems. The near-Shoemaker spacecraft orbited asteroid Eros, which has no moon, but provided detailed information about asteroid composition and structure that helped interpret observations of binary systems. The Dawn mission visited the large asteroids Vesta and Ceres, also moonless, but revealed the complex geology of these protoplanets. Future missions specifically targeting binary asteroids will provide unprecedented insights into these systems. The existence of asteroid moons has practical implications beyond pure science. Some near-Earth asteroids pose potential collision hazards to Earth, and understanding whether they have moons affects how we might deflect them if necessary. A binary asteroid system behaves differently than a single asteroid when subjected to external forces. The NASA DART mission, launched in 2021, deliberately crashed a spacecraft into Dimorphos, the moon of the asteroid Didymos, to test whether kinetic impacts could alter an asteroid's orbit, a potential planetary defense technique. The mission successfully changed Dimorphos's orbital period, demonstrating that asteroid moons respond to impacts in measurable ways. The orbital dynamics of asteroid moon systems are surprisingly rich because the gravitational fields are so weak. Other forces become relatively more important. Solar radiation pressure, the physical push exerted by sunlight, can perturb asteroid moon orbits significantly over time. The orbits slowly evolve, sometimes becoming more circular, sometimes more elliptical, depending on the specific configuration. Tidal forces between the asteroid and its moon, though tiny, gradually exchange angular momentum, causing the moon to migrate inward or outward over millions of years, potentially leading to eventual escape or collision. Triple asteroid systems exist as well, where one asteroid has two moons, or where three similarly sized bodies orbit their common center of mass. The asteroid Sylvia, about 260 kilometers in diameter, has two known moons named Romulus and Remus, discovered in 2001 and 2004 respectively. Romulus orbits at about 1,360 kilometers from Sylvia, with an orbital period of 3.6 days. Remus orbits closer, at about 710 kilometers, with a period of 1.4 days. These multiple moon systems provide natural laboratories for studying gravitational dynamics in the weak field limit. The study of asteroid moons illuminates the processes that operated during planet formation. Planets grew through collisions and mergers of smaller bodies, asteroids, and planetesimals. Understanding how these small bodies interact, collide, capture each other, and form bound systems helps us understand the early stages of planet formation. Every asteroid moon is a relic of these ancient processes, a small-scale version of the interactions that built planets from swarms of orbiting debris billions of years ago. The discovery that asteroids can have moons transformed them from simple rocks floating in space into complex, evolving systems with their own orbital dynamics, formation histories, and future fates. These tiny moons orbiting tiny worlds demonstrate that the fundamental laws of gravity and motion operate at all scales, creating structure and dynamics from the largest galaxy clusters down to kilometer-sized rocks tumbling through the asteroid belt. Each small moon a reminder that even the weakest gravity can bind objects together across the emptiness of space. How extraterrestrial plants could photosynthesize. Photosynthesis, the process by which plants, algae, and certain bacteria capture light energy and convert it into chemical energy, powers most of Earth's ecosystems. Green plants absorb sunlight, split water molecules, combine carbon dioxide from the air with hydrogen from the water, and produce sugars while releasing oxygen as a byproduct. This process transformed Earth's atmosphere from oxygen-poor to oxygen-rich over billions of years, enabling the evolution of complex animal life. Photosynthesis seems so central to life that we naturally wonder whether alien plants on distant worlds would photosynthesize in similar ways. The answer is nuanced. While capturing energy from starlight would likely be advantageous for life on any illuminated world, the specific chemistry and mechanisms of alien photosynthesis would differ dramatically depending on the star's properties, atmospheric composition, available pigments, and evolutionary history of each world. On Earth, photosynthesis centers on chlorophyll, a complex molecule containing magnesium at its center, surrounded by a ring structure that absorbs light strongly in the red and blue portions of the spectrum while reflecting green light, which is why plants appear green. Chlorophyll's absorption spectrum is not random but reflects the properties of sunlight. Our Sun is a yellow dwarf star with a surface temperature around 6,000 degrees Celsius, emitting light most strongly in the visible portion of the spectrum that our eyes evolved to see, with peak emission in the green-yellow range. Plants evolved pigments that absorb the abundant wavelengths while reflecting the less useful portions. But most stars in the galaxy are red dwarfs, cooler, smaller stars with surface temperatures around 3,000 degrees that emit most of their light in the red and infrared portions of the spectrum. A planet orbiting in the habitable zone of a red dwarf would receive much less visible light and far more infrared radiation than Earth receives from our Sun. Photosynthetic organisms on such a world would need to adapt to this shifted spectrum, likely evolving pigments that absorb infrared light rather than visible light. Capturing infrared photons presents challenges because each infrared photon carries less energy than a visible light photon. On Earth, chlorophyll uses 2 photons, absorbed at different stages of photosynthesis, to extract enough energy to split water molecules, which requires significant energy input. With lower energy infrared photons, alien photosynthesis might need to capture 3 or even 4 photons per reaction to gather sufficient energy, making the process less efficient. However, red dwarf stars are extremely common and extremely long-lived, shining for trillions of years compared to the Sun's 10 billion year lifespan. So even if photosynthesis is less efficient under red dwarf light, organisms would have enormous amounts of time to evolve and adapt. The pigments that absorb infrared light would likely appear black or very dark to human eyes because they would absorb nearly all visible light in addition to infrared. A forest on a red dwarf planet might be covered in black vegetation, maximizing absorption of every available photon from the dim red star. This is the opposite of Earth's green plants, which reject green light as insufficiently useful. On a planet where photons are precious, wasting any light would be disadvantageous, so evolution would favor organisms that capture everything. Conversely, planets orbiting hot, bright blue or white stars would receive intense ultraviolet radiation, along with visible and infrared light. Ultraviolet photons carry high energy, potentially too much energy, as UV light damages DNA and proteins. Photosynthetic organisms on such worlds might evolve pigments that specifically avoid ultraviolet absorption, reflecting or dissipating UV light while capturing only visible wavelengths. Or they might evolve protective mechanisms, UV-absorbing compounds in outer cell layers, extremely efficient DNA repair systems, or pigments that can safely handle high-energy photons by converting excess energy into heat or fluorescence. The color of alien plants would thus depend on their star's spectrum. Under orange K-type stars, plants might be red or orange, reflecting the most common light while absorbing other wavelengths. Under blue stars, plants might be yellow or orange. The specific colors would depend not just on what light is available, but also on what pigments evolution happens to discover and what combination of wavelengths provides optimal energy capture. Multiple pigments working together might be advantageous. On Earth, plants contain several pigments beyond chlorophyll, carotenoids, that absorb blue and green light, appearing yellow, orange, or red, and other accessory pigments that expand the range of useful wavelengths. These accessory pigments capture light that chlorophyll misses and transfer the energy to chlorophyll for use in photosynthesis. Alien plants might evolve even more diverse pigment systems, with perhaps 5 or 10 different pigments, each specialized for different wavelength ranges, collectively capturing a broader spectrum than Earth's photosynthetic organisms manage. The electron transport chains that actually convert light energy into chemical energy might use different chemistry than Earth's photosynthesis. On Earth, photosynthesis splits water molecules to extract electrons, releasing oxygen gas as waste. But water splitting is energetically demanding. It requires significant light energy input. An alien photosynthesis might use different electron donors that are easier to oxidize than water. Hydrogen sulfide, for instance, is easier to split than water and was likely used by early photosynthetic bacteria on Earth before oxygen-producing photosynthesis evolved. A planet with abundant hydrogen sulfide might develop photosynthetic life that remains at this stage indefinitely, producing elemental sulfur rather than oxygen as waste. Iron compounds, organic molecules, or even molecular hydrogen could serve as electron donors in alternative photosynthetic pathways. Each would produce different waste products. Iron photosynthesis might precipitate iron oxides. Organic-based photosynthesis might produce various carbon compounds, and hydrogen-based photosynthesis might produce protons that combine with other elements. None of these would generate an oxygen-rich atmosphere, demonstrating that photosynthesis doesn't necessarily equal oxygen production. The carbon source might also vary. Earth plants use carbon dioxide from the atmosphere as their carbon source, but CO2 concentrations vary dramatically across different worlds. Venus has a thick CO2 atmosphere, but is far too hot for life as we know it. Mars has thin atmosphere that's mostly CO2, but overall, CO2 availability is low due to the low pressure. A planet with very low atmospheric CO2 might require photosynthetic organisms that can concentrate and capture CO2 extremely efficiently, perhaps with specialized structures or enzymes far more effective than Earth's plants possess. Alternatively, alien photosynthesis might use carbon sources other than CO2. Carbon monoxide, methane, or even dissolved bicarbonate in water could provide carbon for building organic molecules. Each source would require different enzymatic machinery and would produce different end products. Methane-based photosynthesis might produce more complex hydrocarbons, essentially reversing the process that creates methane on Earth. ICO-based photosynthesis might build organic molecules through different chemical pathways than CO2-based photosynthesis uses. The physical structure of alien photosynthetic organisms might differ radically from Earth's plants. Trees evolved on land where structural support is needed to compete for sunlight, growing tall to shade competitors. But on a planet with perpetual dense cloud cover, blocking direct sunlight and providing only diffuse illumination, there would be no advantage to height. All locations would receive similar light levels. Plants might remain low-growing, perhaps forming dense mats rather than tall structures. On a planet with a very thin atmosphere, providing minimal structural support, perhaps Mars if it ever hosts photosynthetic life, organisms might need to be extremely sturdy and low-profile to withstand wind without atmospheric cushioning. Or on a high-gravity world, the structural challenges of growing tall might be prohibitive, keeping photosynthetic organisms close to the ground in spreading horizontal forms rather than vertical trees. Aquatic photosynthesis might dominate on ocean worlds. Earth's oceans contain vast amounts of photosynthetic organisms, phytoplankton, algae, and photosynthetic bacteria that drift or swim in the water column, capturing sunlight in the upper illuminated layers. On a world covered entirely by ocean, with no dry land, all photosynthesis would necessarily be aquatic. These organisms might evolve greater efficiency at capturing dim light filtered through water, or might develop gas-filled structures to regulate their depth, staying in the optimal light zone. Deep-sea photosynthesis might even be possible using not sunlight, but the faint light produced by hydrothermal vents or bioluminescence. On Earth, some photosynthetic bacteria near deep-sea vents use the faint thermal radiation from the hot vent fluids. This produces very little energy, but it demonstrates that photosynthesis isn't absolutely dependent on sunlight. An alien world with extensive hydrothermal activity might develop photosynthetic life that uses volcanic light, living in eternal darkness sustained by geothermal rather than solar energy. Bioluminescence-powered photosynthesis could create bizarre ecological cycles where organisms generate light through chemical reactions, other organisms use that light for photosynthesis, and the products of photosynthesis support the light-generating organisms. This would be less efficient than using a star's light directly. But on a rogue planet drifting through interstellar space with no star, such a system might be the only way photosynthesis could exist at all. The efficiency of photosynthesis varies greatly on Earth, with most plants converting only 1 to 2% of incoming light energy into chemical energy stored in sugars. This low efficiency reflects various constraints and trade-offs in the photosynthetic machinery. Alien photosynthesis might achieve higher efficiency through different molecular mechanisms, different pigment arrangements, or different metabolic pathways. Alternatively, on worlds where light is extremely dim, even 1 or 2% efficiency might be insufficient, driving evolution toward photosynthetic systems that capture and convert light more effectively, perhaps achieving 5 or 10% efficiency through molecular innovations not present on Earth. Timescales of photosynthesis might differ on other worlds. Earth's photosynthesis operates on timescales of milliseconds to seconds for individual reactions, constrained by the speed of enzyme reactions at Earth's temperatures. On a very cold world, reaction rates would be much slower. Photosynthesis might take minutes or hours for reactions that complete in seconds on Earth. This would mean slower growth rates and organisms that live life in slow motion from our perspective. On a hot world, reactions might proceed faster, allowing rapid photosynthesis and potentially faster growth, though this would also require dealing with the instability of biological molecules at high temperatures. The evolution of photosynthesis on Earth took hundreds of millions of years, with simpler forms appearing first and the complex, oxygen-producing photosynthesis we see in plants evolving later. On alien worlds, the evolutionary trajectory might differ. Perhaps photosynthesis evolves quickly, becoming established within the first billion years of life's appearance. Or perhaps it never evolves at all, with life remaining dependent on chemical energy from geological processes rather than light energy. Photosynthesis, while extremely useful, is not inevitable. It requires specific evolutionary innovations, including light-sensitive pigments, electron transport machinery, and carbon-fixing enzymes. A planet might have abundant life that never discovers photosynthesis, remaining microbial and chemosynthetic indefinitely. The seasonal variations on alien worlds would influence photosynthetic strategies. A planet with extreme axial tilt might experience dramatic seasonal variations in light availability, requiring photosynthetic organisms to either hibernate during dark seasons, store energy during bright seasons, or maintain alternative metabolic modes that don't require light. A tidally locked planet with one side permanently facing its star would have a permanent light side and permanent dark side, with photosynthesis possible only on the lit hemisphere or in the twilight zone between light and dark. The atmospheric chemistry would affect what wavelengths reach the surface. Earth's ozone layer absorbs harmful ultraviolet light, preventing it from reaching the surface. A planet without an ozone layer would expose surface organisms to intense UV, requiring either UV protective mechanisms or restriction of photosynthetic life to water, which naturally blocks UV. A planet with a different atmospheric composition, perhaps with sulfur compounds, nitrogen oxides, or exotic hazes, would filter light differently, creating different wavelengths available at the surface, and thus different optimal pigments for photosynthesis. How extraterrestrial plants could photosynthesize encompasses a vast range of possibilities shaped by stellar spectra, atmospheric filtering, available chemistry, and evolutionary contingency. From black plants absorbing every photon under dim red suns to colourful organisms reflecting abundant high-energy light under bright blue stars. From water-splitting oxygen producers to hydrogen sulfide users releasing sulfur. From rapid tropical growth to slow cold world metabolism, alien photosynthesis would adapt to each world's unique conditions while performing the same basic function, capturing light energy and converting it into chemical energy that powers ecosystems, potentially creating oxygen-rich atmospheres, modifying planetary chemistry in detectable ways, and revealing through their presence that life has discovered on distant worlds what it discovered on Earth. That starlight, properly harnessed through molecular machinery, shaped by billions of years of evolution, can power the chemical reactions that sustain living things, turning distant stars into energy sources for biology across the galaxy. How life could exist on other planets. For billions of years, Earth has been teeming with life, from microscopic bacteria in the deepest ocean trenches to massive blue whales swimming through the seas, from fungi spreading through forest soil to humans building cities and reaching for the stars. But Earth is just one planet orbiting one star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. The question that haunts astronomers, biologists, and anyone who has ever looked up at the night sky is simple yet profound. Could life exist somewhere else? And if it does, what would it need to survive? The search for life beyond Earth begins with understanding what life actually requires. On Earth, all known life shares certain fundamental characteristics. Life requires liquid water as a solvent, a medium in which chemical reactions can occur. It needs a source of energy, whether from sunlight through photosynthesis or from chemical reactions in deep-sea hydrothermal vents. It requires raw materials, elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, that form the building blocks of proteins, DNA, and cell membranes. And it needs time, stable conditions lasting long enough for life to emerge from non-living chemistry and evolve into complex forms. Water stands out as the most critical requirement for life as we know it. Water is an exceptional solvent, capable of dissolving more substances than almost any other liquid. Its unique properties, remaining liquid across a wide temperature range, expanding when it freezes, having strong surface tension, make it ideal for biochemistry. Water molecules interact with each other and with other molecules in ways that facilitate the complex chemistry life requires. Every known organism on Earth, from the simplest bacterium to the most complex animal, depends on liquid water. This dependence on water defines what astronomers call the habitable zone around every star, the range of distances where a planet's surface temperature allows water to remain liquid. For our Sun, this zone extends roughly from just inside Earth's orbit to just beyond Mars. Venus orbits too close. Despite having had water in its distant past, the intense solar heating drove a runaway greenhouse effect that boiled away the oceans and left a hellish world with surface temperatures hot enough to melt lead. Mars orbits near the outer edge, cold enough that most water exists as ice, though liquid water might occasionally form in certain locations under special conditions. But the habitable zone looks different around different types of stars. Red dwarf stars, the most common stars in the galaxy, are much cooler and dimmer than our Sun. Their habitable zones lie much closer in. A planet might orbit only a few million miles from its star, yet still maintain temperatures suitable for liquid water. This close orbit creates challenges. The planet would likely become tidally locked, with one side permanently facing the star in eternal daylight, while the other freezes in perpetual darkness. Red dwarfs also tend to be more active, producing powerful flares that could strip away planetary atmospheres. Yet despite these challenges, red dwarfs are so numerous and long-lived, some will shine for trillions of years, that they represent countless opportunities for life to emerge. Larger, hotter stars have habitable zones farther out, but these stars burn through their fuel quickly, living only millions or billions of years rather than the tens of billions of years that red dwarfs enjoy. This might not provide enough time for complex life to evolve. On Earth, life emerged relatively quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. Intelligence and technology took even longer. A planet orbiting a massive, short-lived star might develop microbial life, but never progress beyond that before its star exhausts its fuel and dies. The atmosphere plays a crucial role in making a planet habitable. Earth's atmosphere provides pressure that keeps water liquid at the surface. Without atmospheric pressure, water would instantly boil away in the vacuum of space or freeze solid at low temperatures. The atmosphere also provides greenhouse warming. Without it, Earth's average temperature would be well below freezing despite being in the habitable zone. Too little greenhouse effect and a planet freezes. Too much and it becomes an inferno like Venus. The balance must be just right. Planetary mass matters significantly. A planet too small cannot hold onto an atmosphere. Its weak gravity allows atmospheric gases to escape into space. Mars demonstrates this problem. Mars once had a thicker atmosphere and liquid water flowing on its surface, carving the river valleys and lake beds that spacecraft have photographed. But Mars is only about 11% of Earth's mass, and over billions of years, its atmosphere gradually escaped. The loss accelerated because Mars lacks a strong magnetic field to shield the atmosphere from the solar wind, the stream of charged particles from the Sun that can strip away atmospheric gases from unprotected planets. A planet too large faces different problems. If a planet grows massive enough, it begins capturing hydrogen and helium directly from the protoplanetary disk during formation, becoming a gas giant like Jupiter rather than a rocky world with a solid surface. Some theories suggest that planets slightly more massive than Earth, called super-Earths, might actually be better for life than Earth itself. Their stronger gravity could hold thicker atmospheres, providing more greenhouse warming and allowing habitable zones to extend farther from their stars. Their larger size might also mean more volcanic activity, recycling nutrients and maintaining atmospheric composition over longer timescales. Plate tectonics, the process by which Earth's crust is broken into plates that move, collide, and subduct beneath each other, might be essential for long-term habitability. Plate tectonics regulates Earth's climate through the carbon cycle. When carbon dioxide accumulates in the atmosphere, chemical weathering of rocks gradually removes it, and subduction carries carbonate minerals deep into the mantle, where heat releases the carbon dioxide back through volcanic eruptions. This cycle acts as a thermostat, preventing runaway greenhouse or icehouse conditions. Without plate tectonics, a planet might lose this regulatory mechanism, making long-term habitability more difficult. But life is remarkably adaptable, and the conditions necessary for life might be far more flexible than our Earth-based experience suggests. On Earth, extremophiles, organisms that thrive in extreme environments, have shattered assumptions about where life can exist. Bacteria live in boiling hot springs at temperatures exceeding 200 degrees Fahrenheit. Microorganisms thrive in the frigid lakes beneath the Antarctic ice. Life exists in hypersaline lakes many times saltier than the ocean, in acidic pools with pH levels that would dissolve metal, and in alkaline lakes caustic enough to burn skin. These extremophiles prove that life can adapt to conditions that would seem utterly hostile. Deep-sea hydrothermal vents host entire ecosystems based not on sunlight, but on chemical energy. Bacteria oxidize hydrogen sulfide and other chemicals spewing from the vents, and entire food chains build upon these chemosynthetic microbes. This discovery revolutionized thinking about where life could exist. A planet doesn't need sunlight reaching its surface to support life. Chemical energy from geological processes suffices. This realization expanded the search for life to include places like Jupiter's moon Europa and Saturn's moon Enceladus, which have subsurface oceans kept liquid by tidal heating. With no sunlight penetrating miles of surface ice, life might not even require a planet's surface. Europa and Enceladus demonstrate that subsurface oceans beneath ice shells can persist for billions of years. These hidden oceans might contain hydrothermal vents similar to those on Earth's ocean floor, providing chemical energy and raw materials for life. Enceladus actively vents water vapor, organic molecules, and salts into space through cracks in its ice, material that spacecraft have flown through and analyzed. The presence of organic molecules and evidence for hydrothermal activity suggests that Enceladus has at least some of the ingredients necessary for life. Titan, Saturn's largest moon, presents an entirely different possibility. Titan is the only moon in the solar system with a thick atmosphere, and it has lakes and rivers on its surface, but they're filled with liquid methane and ethane rather than water. The surface temperature, at about -300 degrees Fahrenheit, is far too cold for liquid water, but some scientists speculate that life might use liquid methane as a solvent instead of water, with biochemistry based on different chemical reactions more suited to cryogenic temperatures. Such life would be utterly alien, built on completely different principles than Earth's biology, but the basic requirements, a liquid solvent, chemical reactions, energy sources, might still allow life to emerge. The possibility of silicon-based life has long fascinated scientists and science fiction writers. Silicon sits directly below carbon in the periodic table and shares many chemical properties. Both form 4 chemical bonds, allowing them to create complex molecules. But silicon-based molecules are generally less stable and less diverse than carbon-based ones, particularly in the presence of water, which tends to break down silicon compounds. In environments without water, perhaps on a world with liquid hydrocarbons or even molten sulfur, silicon-based biochemistry might be possible, though it would function very differently from life on Earth. Life could potentially use different genetic molecules than DNA and RNA. These molecules store and transmit genetic information using a sugar phosphate backbone with nitrogen-based molecules attached. But chemists have synthesized alternatives called XNAS, xenonucleic acids, that use different sugars or even different backbone structures entirely. These artificial genetic molecules can store information and undergo evolution through selection, suggesting that life elsewhere might have invented entirely different solutions to the problem of heredity. Timescales matter enormously for life's emergence and evolution. On Earth, simple life appeared relatively quickly after conditions became favourable, perhaps within a few 100 million years of Earth's formation. This suggests that the transition from non-living chemistry to living organisms might not require unusual conditions or extraordinary luck. But the transition from simple microbes to complex multicellular organisms took vastly longer, roughly 3 billion years. The development of intelligence and technology required nearly all of Earth's history. A planet might easily develop microbial life, but remain stuck at that level indefinitely if conditions don't favour the evolution of complexity. Some planets might develop life, but lose it. Mars almost certainly had more favourable conditions for life billions of years ago when it was warmer and wetter. If life emerged during that time, it might have gone extinct when Mars lost most of its atmosphere and water, or it might persist in subsurface refuges where liquid water still exists in aquifers deep underground. Venus might have had habitable surface conditions early in its history before the runaway greenhouse effect transformed it into the hellscape it is today. Any life that emerged would have been sterilized, leaving no trace. Rogue planets, worlds ejected from their planetary systems to wander interstellar space, might still harbor life, despite receiving no light from any star. If a rogue planet is massive enough to retain a thick atmosphere, and if it has enough radioactive elements in its interior to provide heat, it could maintain liquid water beneath an ice shell indefinitely. Such planets would be invisible to most detection methods, dark worlds drifting through the galaxy, potentially harbouring biospheres in their hidden oceans. Binary star systems, where two stars orbit each other, comprise about half of all stellar systems. Planets in these systems could orbit both stars at a large distance, experiencing light from two suns, or orbit one star closely while the other remains distant. Either configuration could potentially support habitable planets, though the complex gravitational dynamics make stable orbits more difficult to achieve and maintain over billions of years. The discovery of thousands of exoplanets has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. Super-Earths, a planet type absent from our solar system, appear to be common. Some systems pack multiple planets into orbits closer than Mercury's. This diversity suggests that habitable worlds might exist in configurations we haven't imagined, orbiting in stable zones within systems that look nothing like our own. Life could exist on other planets through countless permutations of chemistry, energy sources, solvents, temperatures, and planetary conditions. It might be carbon-based like us, or built from silicon or other elements. It might use water or methane or ammonia or substances we haven't considered. It might photosynthesize under a red sun or derive energy from chemical reactions in lightless seas beneath miles of ice. The universe is vast, ancient, and filled with planets, and the basic ingredients for life, elements forged in stars, energy from stellar radiation or geological processes, and the simple passage of time exist everywhere. Whether life has taken advantage of these opportunities elsewhere remains the greatest unanswered question in science, but the conditions that could allow it exist on countless worlds scattered throughout the cosmos. How gravity bends light in space. Light travels in straight lines through empty space, or at least that's what our everyday experience suggests. A laser beam shoots across a room in a perfectly straight path. Starlight reaches Earth from distant stars without deviating from its course. But this intuition breaks down when gravity becomes involved. In the presence of massive objects, light follows curved paths, bending around stars, galaxies, and even clusters of galaxies in ways that reveal one of the most profound insights about the nature of space, time, and gravity itself. The story begins with Albert Einstein's general theory of relativity, published in 1915, which fundamentally reimagined what gravity is. Newton had described gravity as a force. Masses attract each other across distance through some invisible pull. Einstein proposed something radically different. Gravity, he suggested, is not a force at all, but rather a consequence of the geometry of space-time itself. Massive objects don't pull on other objects. Instead, they warp the fabric of space-time around them, and objects simply follow the straightest possible paths through this curved geometry. Imagine space-time as a stretched rubber sheet. Place a bowling ball on the sheet, and it creates a depression, warping the flat surface into a curved shape. Now roll a marble across the sheet near the bowling ball. The marble's path curves as it moves through the depression, not because the bowling ball is pulling on it, but because the surface itself is curved. The marble is still following the straightest path it can, what mathematicians call a geodesic, but in curved space, straight lines look curved to outside observers. This is what happens with light near massive objects. The light is following a geodesic through space-time, travelling along the straightest possible path. But because space-time itself is curved by the presence of mass, that path appears curved when viewed from our perspective. The light isn't being pulled by gravity in the Newtonian sense. It's simply following the geometry of space-time, which has been warped by mass. The amount of bending depends on two factors: the mass of the object doing the bending and how close the light passes to that mass. More massive objects create deeper curves in space-time, causing more dramatic bending. Light passing closer to a mass experiences stronger curvature than light passing farther away. For most objects we encounter in daily life, this bending is utterly negligible, far too small to detect. Even for something as massive as Earth, the bending of light is minuscule. A beam of light grazing Earth's surface would bend by less than 1,000th of a degree. But consider the Sun. With a mass 333,000 times greater than Earth, the Sun creates a significant warp in space-time around it. Light from a distant star passing close to the Sun's surface is deflected by about 1.75 arc-seconds, a tiny angle equal to roughly the width of a quarter viewed from 2 miles away, but measurable with careful observations. This prediction of general relativity was first confirmed during a solar eclipse in 1919, when stars near the Sun's position in the sky appeared slightly displaced from their normal locations. The Sun's gravity had bent their light as it passed by, making the stars appear to be in slightly different positions than they actually were. This gravitational bending of light becomes dramatically more pronounced around more massive and compact objects. A neutron star containing more mass than the Sun, compressed into a sphere only about 12 miles across, creates such severe space-time curvature that light from the far side of the star can bend around it and reach an observer on the opposite side. You could theoretically see more than half of the star's surface at once because light from behind curves around to the front. Black holes represent the extreme limit of gravitational light bending. At the event horizon of a black hole, space-time is curved so severely that light emitted outward from that surface is bent back inward. The escape velocity at the event horizon equals the speed of light, which is another way of saying that space-time curvature there is so extreme that even light following its straightest possible path still curves back toward the black hole. Just outside the event horizon, there's a region called the photon sphere, where light can orbit the black hole in unstable circular paths, bent continuously by the intense curvature of space-time. The shadow of a black hole, the dark region we see in images like the famous Event Horizon Telescope picture of M87's supermassive black hole, exists because of this extreme light bending. Light that passes close enough to the black hole is captured, unable to escape, creating a dark silhouette. The bright ring surrounding this shadow is light from the accretion disk that has been bent and focused by the black hole's gravity, with some photons having orbited partway around the black hole before reaching the observer, creating multiple images overlaid on each other. Gravitational lensing occurs when light from a distant object passes near a massive object on its way to Earth. The massive object acts as a lens, bending the light and focusing it toward Earth, just as a glass lens bends and focuses light. Galaxies and galaxy clusters containing hundreds of billions or even trillions of times the Sun's mass are particularly effective gravitational lenses. When a massive galaxy cluster lies between Earth and a more distant galaxy, the cluster's gravity bends light from the background galaxy, often creating multiple images, arcs, or even complete rings. Einstein predicted a specific case called an Einstein ring, which forms when the lensing mass, the background light source, and the observer are perfectly aligned. In this configuration, the background object's light is bent equally in all directions around the lensing mass, creating a circular ring of light. Perfect Einstein rings are rare because perfect alignment is unlikely, but numerous partial rings and arcs have been observed where the alignment is close but not exact. Strong gravitational lensing creates multiple images of the same background object. Light from the source can take different paths around the lensing mass, arriving at Earth from different directions. An observer sees the same galaxy or quasar in multiple locations in the sky simultaneously, each image distorted differently depending on the path the light took. By analysing these multiple images, their positions, brightness and distortions, astronomers can map out the distribution of mass in the lensing object, including the dark matter that can't be seen directly. One of the most famous examples of gravitational lensing revealed itself in the Hubble Deep Field images. A massive galaxy cluster acts as a natural telescope, magnifying and brightening galaxies far behind it. Some of the most distant galaxies ever observed were discovered this way, their light amplified by gravitational lensing to the point where even these incredibly faint, distant objects become visible. Without the magnification provided by the intervening cluster's gravity, these galaxies would be too faint to detect, even with our most powerful telescopes. Weak gravitational lensing is a more subtle effect. Rather than creating obvious multiple images or dramatic arcs, weak lensing slightly distorts the shapes of background galaxies. Each galaxy is stretched and sheared by a tiny amount, usually only a few percent. Individual distortions are impossible to distinguish from the galaxy's natural shapes, but by measuring the shapes of thousands or millions of galaxies and looking for statistical patterns in their distortions, astronomers can map out the distribution of matter, including dark matter, along the line of sight. This technique has become one of the most powerful tools for studying dark matter distribution in the universe. Gravitational lensing also affects the apparent brightness of objects. When a massive object passes between Earth and a more distant star, the foreground object's gravity can focus the background star's light, temporarily brightening it. This gravitational microlensing is used to detect exoplanets. When a star passes in front of another star, the foreground star's gravity creates a brief brightening lasting days to weeks. If the foreground star has a planet, the planet's gravity creates an additional, brief spike in brightness, revealing its presence even though the planet itself is far too faint to see directly. The time light takes to travel along different paths around a gravitational lens can vary. Light taking a longer path around one side of a lensing galaxy arrives later than light taking a shorter path around the other side. For variable sources like quasars, which change in brightness over time, this time delay becomes observable. A brightening in one image of a lensed quasar will appear days, weeks, or months before the same brightening appears in another image, the delay corresponding to the difference in light travel time along the different paths. Measuring these time delays allows astronomers to determine distances to the lensed objects and constrain cosmological parameters like the universe's expansion rate. Space-time curvature near massive objects doesn't just bend light spatially, it also affects light's frequency through gravitational redshift. Light climbing out of a gravitational well loses energy, shifting to longer wavelengths and lower frequencies. Photons emitted from the surface of a white dwarf, neutron star, or near a black hole arrive at Earth redshifted compared to identical photons emitted far from any massive object. This gravitational redshift is distinct from the Doppler shift, caused by motion. It's a consequence of how time itself runs slower in stronger gravitational fields. The ability of gravity to bend light provides one of the most direct ways to test general relativity. Every observation of gravitational lensing confirms Einstein's predictions about how spacetime curvature works. The precise angles at which light bends, the patterns of multiple images, the time delays between images, and the gravitational redshift all match the predictions of general relativity with remarkable accuracy. Alternative theories of gravity make different predictions, and so far, every test has vindicated Einstein's century-old theory. Gravitational lensing has become an essential astronomical tool. It allows us to study the distribution of dark matter by observing how it lenses background galaxies. It magnifies distant galaxies, enabling studies of the early universe that would otherwise be impossible. It reveals exoplanets orbiting distant stars. It measures cosmic distances and the expansion rate of the universe. All of this is possible because massive objects warp spacetime, and light faithfully follows the curves and valleys of that warped geometry. The universe is filled with matter, and that matter curves spacetime everywhere. Light from the most distant galaxies has travelled billions of years to reach Earth, passing countless galaxies, galaxy clusters, and vast expanses of dark matter along the way. Every massive structure the light passes deflects it slightly, creating a cosmic hall of mirrors where every photon's path is bent and redirected many times. The images we see in our telescopes are not straight-line projections from their sources, but rather the accumulated result of countless tiny deflections as light navigates the curved spacetime of our universe. The geometry of the universe itself, on the largest scales, also affects how light travels. If the universe has overall positive curvature, like the surface of a sphere, light paths will eventually converge. If it has negative curvature, like a saddle shape, light paths diverge. Current observations suggest the universe is nearly flat on the largest scales, meaning that, on average, over distances spanning billions of light years, light travels in straight lines. But locally, around every massive object from planets to galaxy superclusters, spacetime curves, and light follows those curves, revealing the intimate connection between matter geometry and the paths that light traces through the cosmos. How aliens could breathe. Different atmospheres. When we imagine aliens visiting Earth in science fiction, they often step out of their spacecraft and breathe our air without difficulty, or they wear helmets and breathing apparatus because our atmosphere is toxic to them. Both scenarios recognize a fundamental truth. The atmosphere that sustains one form of life might be useless or deadly to another. On Earth, oxygen is essential for most complex life, powering the high-energy metabolisms of animals through cellular respiration. But oxygen wasn't always abundant in Earth's atmosphere, And even today, many organisms live without it, thriving in environments where oxygen is scarce or absent. Understanding how aliens could breathe different atmospheres means understanding the relationship between atmospheric gases and metabolism, the chemistry of energy extraction, and the remarkable adaptability that evolution can produce when organisms face different atmospheric conditions. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, water vapor, and other gases. This composition seems normal because it's all we've known, but it's actually quite unusual from a cosmic perspective. Oxygen is highly reactive. It combines readily with many elements, forming oxides that are stable and chemically inert. Free oxygen shouldn't persist in a planet's atmosphere for long unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria capture sunlight and use its energy to split water molecules, releasing oxygen as a byproduct. Without life constantly producing oxygen, Earth's atmosphere would gradually lose its oxygen as the gas reacted with rocks, metals, and organic molecules, eventually leaving an atmosphere dominated by nitrogen and carbon dioxide. For the first 2 billion years, or more of Earth's history, the atmosphere contained very little free oxygen. Early life evolved in this oxygen-poor world, using different metabolic pathways that didn't require oxygen. Even today, many organisms live in oxygen-free environments, deep in ocean sediments, in the intestines of animals, in waterlogged soils, where oxygen cannot penetrate. These anaerobic organisms use alternative molecules as the final electron acceptors in their metabolism. Some use sulfur compounds, reducing sulfate to hydrogen sulfide, the gas that smells like rotten eggs. Others use nitrates, producing nitrogen gas. Still others use carbon dioxide itself, producing methane. These metabolisms are less efficient than oxygen-based metabolism, releasing less energy per molecule of food consumed, but they work well enough to sustain life. An alien planet that never developed photosynthetic life might retain an oxygen-poor atmosphere indefinitely. Life on such a world would necessarily use anaerobic metabolism, breathing gases we would consider unusual or toxic. Hydrogen sulfide, lethal to most Earth animals, could serve as the oxidizing agent in alien metabolism. Organisms might inhale hydrogen sulfide and exhale elemental sulfur or some other sulfur compound. Their biochemistry would be built around sulfur chemistry, the way ours is built around oxygen chemistry. These aliens would find Earth's oxygen-rich atmosphere as toxic as we find hydrogen sulfide. Oxygen would react with their sulfur-based biochemistry, disrupting the carefully balanced chemical reactions that keep them alive. Methane represents another possibility. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, and it exists as a gas at temperatures where water is liquid. Some Earth organisms produce methane as a waste product of their metabolism, and these methane-producing microbes, called methanogens, thrive in oxygen-free environments, like swamps, rice paddies, and the digestive systems of cattle. Methane is flammable in the presence of oxygen, but in an oxygen-free atmosphere, it's stable. A planet with abundant methane in its atmosphere might support life that uses methane in its metabolism, perhaps breaking down methane to extract energy or using methane as a raw material to build more complex organic molecules. Titan, Saturn's largest moon, has an atmosphere dense with nitrogen and methane, with no free oxygen. The surface temperature hovers around -180 degrees Celsius, cold enough that water is frozen as hard as rock, while methane exists as liquid in lakes and seas. If life exists on Titan, a big if, but not impossible, it would necessarily be adapted to breathe this nitrogen-methane atmosphere, and might even metabolize in ways that involve liquid methane rather than liquid water. Such organisms would be completely incompatible with Earth's environment. Bringing them to Earth would be like throwing a fish into a furnace. The heat alone would destroy them before oxygen toxicity became an issue. Carbon dioxide-rich atmospheres present another scenario. Venus has an atmosphere that's about 96% carbon dioxide, creating a crushing surface pressure about 90 times Earth's atmospheric pressure, and a runaway greenhouse effect that raises surface temperatures to over 450 degrees Celsius. No life could exist in Venus's current conditions, but a cooler planet with a carbon dioxide atmosphere and might be habitable. Some Earth organisms already tolerate high carbon dioxide levels that would kill humans. Deep-sea hydrothermal vent communities, for instance, experience high carbon dioxide concentrations dissolved in water. Organisms adapted to such environments have specialized biochemistry that allows them to function despite the high carbon dioxide. Aliens from a carbon dioxide-rich world might metabolize in ways that involve carbon dioxide directly. Perhaps they would use carbon dioxide as an oxidizing agent, combining it with hydrogen-rich compounds to extract energy, producing methane or other hydrocarbons as waste products. Or they might use carbon dioxide as a raw material, building organic molecules from carbon dioxide the way plants do, but doing so as part of their metabolic processes rather than as a separate photosynthetic function. These aliens might find oxygen toxic and carbon dioxide essential, the opposite of most Earth animals. Ammonia is another gas that could potentially play a role in alien respiration. Ammonia is toxic to most Earth life, disrupting pH balance and interfering with normal biochemistry. But at lower temperatures, ammonia can exist as a liquid, and some scientists have speculated that ammonia could serve as a solvent for biochemistry on very cold worlds, potentially replacing water. An atmosphere with significant ammonia might support organisms that breathe ammonia, using it in their metabolism in ways we can barely imagine. The chemistry would be entirely different from oxygen-based metabolism, operating through different pathways and producing different waste products. Chlorine and fluorine, both highly reactive halogens, represent more exotic possibilities. These gases are extremely reactive and toxic to Earth life, but that's precisely because they're good at accepting electrons, the same property that makes oxygen useful for metabolism. An organism that evolved in an atmosphere containing chlorine or fluorine might use these gases the way we use oxygen, combining them with food molecules to extract energy. The waste products would be chlorides or fluorides rather than the water and carbon dioxide that Earth animals produce. Such organisms would find Earth's atmosphere lacking. Our oxygen, while reactive, wouldn't fit into their chlorine-based or fluorine-based biochemistry. They would suffocate in our air despite it containing a highly reactive gas. The partial pressure of gases matters as much as their chemical identity. Partial pressure is the pressure contributed by a specific gas in a mixture. For instance, Earth's atmosphere has a total pressure at sea level of about 1 atmosphere, and oxygen makes up 21% of that. So oxygen's partial pressure is about 0.21 atmospheres. Humans need oxygen at roughly this partial pressure to survive. Too little at high altitudes where atmospheric pressure drops and we suffer hypoxia, unable to get enough oxygen into our blood. Too much in pure oxygen at high pressure, and oxygen becomes toxic, causing seizures and lung damage. Aliens would have similar constraints based on their biochemistry. An alien that breathes hydrogen sulfide might need it at a specific partial pressure. Too little, and their metabolism cannot function efficiently. Too much, and it becomes toxic even to them. This means that even if two species breathe the same gas, they might not be able to share the same atmosphere if they require different partial pressures. An alien adapted to breathe oxygen at very low partial pressures, perhaps from a high-altitude environment or a planet with thin atmosphere, might suffocate in Earth's oxygen-rich air, not from lack of oxygen, but from oxygen toxicity. temperature affects which molecules can exist as gases. On Earth, at our range of temperatures, nitrogen, oxygen, carbon dioxide, and water vapor exist as gases, while water also exists as liquid. On a much hotter planet, perhaps one close to its star, gases we don't encounter might be common. Sulfur compounds that are liquids or solids on Earth might be gases on a hot world. Metals like mercury or even iron could exist as vapor in the atmosphere of an extremely hot planet. Life on such a world, if it could exist at all, might breathe exotic gases that would condense into liquids or solids in Earth's relatively cool atmosphere. Conversely, on extremely cold worlds, gases that are common on Earth might be frozen solid. On Pluto, where temperatures drop to around -230 degrees Celsius, nitrogen, which makes up most of Earth's atmosphere, freezes into solid nitrogen ice. Pluto's thin atmosphere consists of nitrogen, methane, and carbon monoxide that sublimates from surface ices when Pluto is closest to the Sun in its elliptical orbit, then freeze back out when Pluto moves farther away. Life on such a cold world would need to breathe gases that remain gaseous at these extreme temperatures, or it would need to exist in warmer subsurface environments where different conditions prevail. The evolution of breathing mechanisms would differ based on atmospheric composition and pressure. On Earth, animals evolved lungs, gills, tracheal systems, and other specialized structures to extract oxygen from air or water. Fish gills expose blood to water flowing past thin membranes, allowing oxygen to diffuse from water into blood. Insect tracheal systems deliver air directly to cells through branching tubes. Mammalian lungs use millions of tiny air sacs to maximize surface area for gas exchange. Each system is optimized for extracting oxygen from Earth's atmosphere or water. Aliens breathing different atmospheres would evolve different respiratory structures optimized for their specific gases. An alien breathing a very dense atmosphere, perhaps with pressures many times Earth's, might have very small respiratory surfaces because gases would diffuse quickly at high pressure. An alien breathing a thin atmosphere might need enormous respiratory organs to capture enough of their necessary gas. An alien breathing a gas that dissolves poorly in their body, fluids might need respiratory pigments, molecules like hemoglobin in our blood, specifically designed to bind and transport their particular gas. Some aliens might not breathe at all in the sense of moving gases in and out of their bodies. Single-celled organisms on Earth absorb oxygen directly through their cell membranes without any respiratory system. An alien with a radically different body plan, perhaps resembling Earth's sponges or fungi more than animals, might absorb needed gases through its entire surface area, rather than through specialized breathing organs. Or an alien might rely entirely on anaerobic metabolism happening within its cells, never needing to extract gases from the environment at all, living on chemical energy stored in molecules absorbed from its surroundings. The possibility of breathing different atmospheres means that habitable zones around stars become more complex. The traditional habitable zone focuses on temperature, the range where liquid water can exist. But a habitability zone could be defined for any solvent and any metabolic gas. There's a methane habitability zone at different temperatures where methane is liquid. There's a hydrogen sulfide habitability zone where that gas exists at suitable pressures. There's an ammonia habitability zone at very cold temperatures. Each zone would support fundamentally different kinds of life adapted to its specific conditions. If humans ever encounter aliens, the atmospheric incompatibility would be one of the first obvious differences. We couldn't share environments without life support equipment. An alien from an ammonia world would need refrigeration and ammonia supplies to survive in Earth's environment. We would need oxygen supplies and temperature regulation to survive in theirs. Even communication would be affected. Sound travels differently in different atmospheric gases. In a dense carbon dioxide atmosphere, sound would be lower pitched and quieter. In a thin hydrogen atmosphere, sound would be higher pitched and travel faster. An alien's voice might be physically impossible for human ears to hear without electronic translation. How aliens could breathe different atmospheres ultimately reflects the diversity of chemistry and the flexibility of evolution. Life adapts to available conditions, and the chemistry that powers metabolism is not limited to oxygen and carbon dioxide. From hydrogen sulfide to methane, from ammonia to chlorine, from thin atmospheres to crushing pressures, from scorching heat to numbing cold, life, if it exists elsewhere, would develop respiratory systems suited to its world's specific conditions, breathing atmospheres that might kill us in seconds, while finding our oxygen-rich air as toxic and alien as we would find theirs, proving that the breath of life can take as many forms as there are worlds scattered across the universe.